Okay, in this video I'm going to continue on with my tutorials on differential equations. This is video number 8 or video 6 in the subsection on power series solutions to differential equations. Specifically, I'm going to show you how to use power series to solve a differential equation. I'm going to give you the theory, and in the coming videos we'll do a couple of examples. So there are 7 videos previous to this, which I suppose all are relevant in one way or another. Video 1 I discussed the classification of differential equations. In video 2 I discussed what power series are used for in terms of, let's say, Fourier series, or comparing them to Fourier series. In video 3 I discussed where power series start. 4 I differentiated power series. 5 I shifted the indices. 6 I multiplied by a function. And in 7 I discussed the characteristic equation, which is what we use to solve a differential equation with constant coefficients, or a second order differential equation with constant coefficients. So let's say, for example, we have the differential equation written on the top right of your screen. So this equation has the variable coefficient p, a function of x, multiplied by the second derivative of y, plus the variable coefficient q of x multiplied by the first derivative, the variable coefficient r of x multiplied by the 0th derivative, and is equal to another variable coefficient t of x. Notice that it's a non-homogeneous equation. So this is the most general is when it's non-homogeneous. And note, by the way, we have variable coefficients. This means that we cannot use the method of the characteristic equation, but rather we must use the method of power series solutions. So the suggestion we make is that the function y, a function of x, can be written as the infinite power series. Note, by the way, it's an infinite power series, so for physical reasons at some point we'll have to truncate it. But it's the infinite power series of the coefficients a sub n times x to the n. Now, just to give us an aside, let's say we have the differential equation where we have x squared times y double prime plus x times q of x times y prime plus r of x times y is equal to t of x. Now, in this particular case, it's most likely we would have to use what's called the method of Frobenius, because if we divide, we'll say, across by, in this case, x squared, it's likely that we'll get a singularity or a pole where we get this divide by 0 scenario at z, or x is equal to 0. So here I've divided across by x squared, and we note that it's not analytic at x is equal to 0. So not analytic means basically we're going to be having a divide by 0 scenario at x is equal to 0. So this occurs when either q of x divided by x or r of x divided by x squared remain as something over a function of x, because when we plug in x is equal to 0, we're going to get a divide by 0 scenario. Now, we're going to assume for the moment that that doesn't happen. So when we don't get something that is not analytic, or when we have an analytic function, we can just let our function y, a function of x, be equal to the infinite sum of a sub n x to the n. The difference is when we use Frobenius, we add another term, we add let's say a small r here, but we don't need to do that for our current requirements. So once again, I've written on the top left of your screen the suggested power series, and we need to calculate the derivatives in order to plug it into our differential equation. So it's very straightforward, differentiating the power series once and then differentiating the power series twice. Note that we can say that in the first derivative we can start at n is equal to 1, and the second derivative we can start at n is equal to 2. And the reason is because the lesser terms are 0 anyway. So let's look at the first derivative, y prime. If we plug in n is equal to 0, we find that the first term is 0 anyway. So we may as well just start the power series at n is equal to 1. Similarly, if you plug in n is equal to 0 and n is equal to 1, for the second derivative we find both of these terms are also 0. So for that reason we start at n is equal to 2. Now, note that all series must start at the same point and have the same exponent. If they don't have the same exponent or don't start at the same point, we are required to shift indices. So you are free to select any start point, but personally I always shift upwards. So I find the the term with the highest coefficient, or the highest power, excuse me, and I shift everything up to that. So if we're looking at our 0th, first and second derivatives, we see that x to the n is the highest power. We have x to the n minus 1 and we have x to the n minus 2. So I discussed shifting indices in the previous video, and we see that we can shift the first and second derivatives up to x to the n, and the actual power series will start now at n is equal to 0. Look at my video on shifting indices if that isn't straightforward for you. Note, if we hadn't let, for example, y prime start at n is equal to 1 and y double prime start at n is equal to 2, the shifting of the indices would be more difficult. So when we can allow the method of regular power series solutions, we always move the indices up as we differentiate. However, with the method of Frobenius, we always start at 0 because the other terms will always be non-zero. Whereas specifically we could move the index with the differentiation because the other terms were 0. But that does not work for the method of Frobenius. So next what we do is we plug back in our new first, second and 0th order derivatives into our differential equation. So I've done that, but I've also factored out the common infinite sum of x to the n. So we see that here's the infinite sum of x to the n, and we're left with all the coefficients. Note, by the way, we have an a sub n plus 2, an a sub n plus 1 and an a sub n here. So I'm sure you know what's going to happen next. We say that the sum can't be 0 because if the sum is 0, then we get the trivial solution where everything is 0. This implies that the sum of the coefficients must be 0, and what we call this is the recurrence relation, or it leads to what we call the recurrence relation. Now often in practice, if you actually look at a real power series, or excuse me, a real differential equation, one of your coefficients, p of x or q of x, will be such that they won't require a shifting of indices. So, you know, that's just what happens very often, and that's what we're going to look at now. Let's say if we went back a page, we said that q of x was equal to x. What that would have meant is that instead of having to shift this particular term up to a of n plus 1, we can just leave it at a of n, and we need to still multiply it by this term n. I'm sure you can accept that. So now if we look closely, we have a sub n plus 2, but we have a sub n and a sub n. But just before we continue, just to confirm we know where this came from, if you go back here, we have the first derivative with respect to x of y. But if I multiply, let's say, by an x here, instead of having a power of n minus 1, I'm going to have a power of x to the n. And I won't have had to adjust anything else. Okay, so I'm just going to, instead of having to shift to a sub n minus 1, I'm still going to have a sub n here like this. So moving on, and from now on it's going to be, I suppose, in many respects fictitious, because I'm trying to show you a general example without plugging in any real figures. So if we just solve this equation for a sub n plus 2 in terms of a sub n, we get what's known as the recurrence relation. So the recurrence relation is written on the top right of your screen, and we still have it in terms of this other variable coefficient r of x. So I'm going to give that a value of positive 1 just now. So the recurrence relation gives you your a sub n's, and once you find out what your a sub n's are, you can fill them in on the left hand side of your screen in the black square brackets, and then you have your total solution, or your final solution. So what we do here in order to calculate the a sub n's is we start plugging in n is equal to 0, 1, 2 or whatever it is. And what we're looking for is to see a pattern, and instead of writing out all the a sub n's, we can just write down a formula for the a sub n's, a better one than this recurrence relation. So I'm not really going to go through this, but you can plug in the values. So let's say I plug in n is equal to 0, well, I'm going to get a sub 2, and n is equal to 1, I'm going to get a sub 3. Generally what will happen is you'll have an a sub 0 and an a sub 1. And as you increment n, you can keep rewriting your next terms in terms of a sub 0 and a sub 1. For example, if we plug in n is equal to 2 here, we're going to get a sub 4. And we already have a value for a sub 2, which we can plug back in and get this in terms of a sub 0. Something similar happens with a sub 5. We can always write it in terms of a sub 1. What appears to be happening here is we're getting two equations. One which has even numbers, this would be even, and one which has odd numbers of n. And we seem to be getting two sets of series. And one has a coefficient of a0, the other has a coefficient of a sub 1. And that's normal to have. And generally what you're going to try and do is put it in some sort of very compact and neat form. Now I'm not going to give you an example of that, but I'm going to tell you the sorts of things you should be looking for. So like I said, you will find that you'll generally get an even and odd solution, one for a0 and one for a sub 1, of the two coefficients. And they determine everything else. And we try and spot a pattern. So first of all, we look for things like factorials. So just very quickly, if we go back, we can see here that even on a sub 4, we already have a factorial. We have 4, 3, 2, 1 on the denominator. And this is a sub 4, so it looks like an n factorial on the bottom. So factorials are everywhere when we solve these differential equations. Note, by the way, that minus 1 to the n gives us plus or minus 1. So we oscillate between positive and negative. But if you look here, a sub 2 is minus, or is negative, a sub 4 is positive, and it can tell you that a sub 6 is going to be negative as well. So this would require a plus or minus, a minus 1 to the n. Also, if we have x, let's say, to the 2n, this only gives us even powers. So it's going to give us x squared, x to the 4, 6, or 8. Similarly, if we have x to the 2n plus or minus 1, it'll give us odd powers. Usually we have x to the 2n minus 1 because that'll give us 1, 3, 5, 7, and 9. So if you're looking to selectively have certain coefficients, you can use either the 2n or the 2n minus 1 coefficient. Now, if you're looking to multiply terms together, they seem to be constantly multiplying, but they're not themselves, say, factorials. You can use the multiplication, or this multiplication symbol, capital pi. So it's like capital sigma, which is summation, but this is multiplication. Now, where you lack terms for a factorial, multiply above and below by the missing terms. Let's say, for example, we had 5 times 4 on the top. So we need, of course, 3 and 2. So multiply by 3 and 2 and 1, and 3 and 2 and 1. And often what you'll get is that you'll get other terms. You might have a 4 down here as well, and you'll end up with something like 5 factorial over 4 factorial. Something along those lines. I'm just giving you the sorts of things you should be looking at in order to come up with your general solution for your a sub n's. But once you do that, you must plug them back into the actual equation, into the power series, and sub them in for the a sub n. And you still multiply by x to the n. So the next videos will be examples, and I hope that they will fix any problems or confusion that you may or may not have. So thanks for watching. Please pass it on to your friends, subscribe to my channel, and you might also give me a comment in the box below. Thank you.